Well, we're going to record this for the sake of people who are not here, but it's going to be kind of a strange class because I'm going to be doing some physical demonstrations. And because of that, you guys that are not here are going to have to sort of imagine it in your mind. And tomorrow you'll actually get to use this equipment and you won't have to imagine quite so much anymore. Yes?
To do physical demonstrations and not just sit on it.
Oh, that'd be delightful. Sure. So Grant is going to video the physical demonstrations and we'll put it up there as an auxiliary video. Fantastic. So I want to talk about a couple things that came up in the homework. You probably saw the unit of energy electron volts in your homework. And of course that was in the reading, but I want to emphasize this point because everybody needs to know it. An electron volt is designed to be an easy unit of energy because very often when we're working with subatomic particles or individual atoms, then we'll have a certain potential difference, maybe 90 volts or something like that. And we want to know how much energy does an electron get as it travels from plus 90 to 0. And of course the answer is 90 electron volts. See how easy that is? So it's convenient if we're working with subatomic particles. But at some point we might have to convert that into joules. And so how do we do that? Well, the unit is literal. It's literally the charge on the electron, 1.6 times 10 to the minus 19 coulombs, times 1 volt, which is a joule per coulomb. So 1 electron volt is 1.6 times 10 to the minus 19 joules. Now, Keitha, in her homework, turned that upside down and figured out the number of electron volts in a joule. So we could probably do that also. 1 joule times 1 electron volt per 1.6 times 10 to the minus 19th joules turns out to be how many electron volts?
6.24 times 10 to the 18.
But see, memorizing 2 numbers is not nearly as convenient as just memorizing the 1. And both of them give you a nice equivalence. Okay, our goal for today is to talk about equipotential lines. But to do that...
Does handle it with care.
Did he smile?
Yeah.
Our goal for today is to talk about equipotential lines. And to do that, we are going to need to talk about measuring voltage. And I'm going to show you some of the gear that electrical engineers use in order to create voltage and measure voltage. What Grant is doing right now is inserting the battery into one of our new voltmeters. I've got some old voltmeters that are also useful. And so I'm going to show you how to use both the analog and the digital voltmeters. Downstairs also digital voltmeters.
That's good. It wasn't that anymore.
Ooh, that's exciting.
Wait, what am I asking for?
Digital voltmeter. However, it looks like standards was limited to batteries. So yeah, I'd just say go ahead and replace the battery.
Okay. The battery was broken inside the package.
Yeah, there's a battery already inserted in it. It was rusted out on the sides and stuff. What happens is the chemicals inside, which are going to be alcohol, leak out and end up interacting with the metal of the case. You often have to destroy contact points, but here it looks like it's limited. Try to use the screwdriver to pry it. Okay, so our story so far has been that we defined electrical potential in terms of potential energy. So the baseline equation that we used in all cases is that potential energy is going to be equal to charge times voltage. Now, out of this comes a lot of different equations. If I'm considering our two particular situations that we talked about a point charge, and we also talked about parallel plates. In the case of point charge, we had to do some calculus, and so I waved my hands and said calculus, calculus. And when we did, we got that the voltage was equal to the constant, to the universal constant K, or Coulomb's constant K, times the charge divided by the distance R from the point. So that if I have a point charge here, I can go out to a distance R and compute the electrical potential just like that. Notice that when we have a point charge, we always take as our 0 point the point out at infinity, so that there is 0 potential at an infinite distance away from the point charge. What that allows us to do, by the way, is to essentially ignore any charges that are far away distant. So if you have a microcoulomb charge sitting on top of your head, then I would consider you to be at a distance that is practically infinite relative to charges, and I would just ignore that microcoulomb charge. For parallel plates, our setup is like so. We have two parallel plates like this, and we're going to charge them up so that this one is plus and this one is minus. And what we discovered by doing math was that the change in voltage between them is equal to negative EV. And the negative sign simply indicates that the electric field is going to be pointing from plus to minus, but my voltage is going to be dropping as we move down these electrical field lines. So that if I set as my 0 point the negative plate here, then my positive plate will have a positive voltage. And that's usually the way that we analyze these parallel plates. So that we're just checking that out. Notice that the change in voltage as I go from plus to minus is 0 minus the negative. Okay. So that was our story yesterday. Today I'd like to show you how that's created and how that's measured. What I have over here is a power supply. No, wrong one.
He said analog.
Digital. Digital power. Oh, is it? Wait, look at that.
Well, one is screwed up, and now I can't
I
find
can
it.
go get a screw.
Yeah. Where's the screw spell?
Yeah.
Can't find it.
Oh, we should share.
All right, well, let me know. But this will do for now. Let's see if we use probe.
Hear that.
So let's see if, oh, the probe is here. Excellent. All right, so what I have over here is a power supply, and the power supply is designed to deliver a constant voltage to the best of its ability. Now, power supply is designed to deliver a constant voltage to the best of its ability. Every power supply is limited in its ability, and what limits it is going to be the number of electrons that it can pump through at any given time. We call that the current. We'll study current in a future lesson. But the main point today is that that power supply is going to have to deliver a certain number of electrons, and if we exceed the number of electrons that the power supply can actually deliver, then rather than allow its voltage to sort of vary, what it will do is just shut off. So this particular power supply is designed to deliver, or was, when it was fresh, designed to deliver 13.8 volts for any current load between 0 and 3 amps. And if I exceed that 3 amps, which basically means I'm trying to pump too many electrons through, it will just turn itself off. So let me show you how the turning off would work before we get going, so that you can, mainly so that you can not be afraid of the power supply here. Notice that I can touch here without any damage to myself because the voltage is only 13.86 volts. Here's a piece of cultural literacy. You basically have to get up to about 30 volts on dry skin before you notice anything. Another piece of cultural literacy. You may or may not know that your landline phones are actually powered by a completely separate power supply from your house, so that if the power goes out, your landline still works. And the voltage difference that drives the phones is 40 volts. So if you touch the plus and minus on a phone power supply, you'll feel a little buzz. And that little buzz is the 40 volt difference between them. So here we go. I've got a 13.86. Now I'm going to connect plus to minus, and when I do, a large amount of current should flow, but look at this. See there? The light just turns off, and that's because the power supply recognizes that it can't source as much current as I want it to. Look at the little indicator light right there. See? Goes off. Because it's not able to source as much current as I want it to, and so it just shuts itself off. But when it's not actually connected together, it's able to produce nominally 13.86 volts. Let's see if our power supply is still in good working order here, since I'm using one of the old ones. And I'm going to measure this. Why don't you guys all come up and watch here. I'm going to do the digital voltmeter first because that is the kind of meter that you're going to be using for the lab tomorrow. And the digital voltmeter is going to have some probes. And these probes are a little stiff, but that's good. We're going to set it to DC volts. You're probably aware that voltage can be supplied in two different ways. One is DC, or direct current, is a constant voltage. And the other way is AC voltage, which is alternating in a sinusoidal pattern. And what comes out of the wall is AC volts, mainly because there was a fight between Edison and Tesla on this issue, and Edison won. And to measure voltage at between any given 2 points, notice that I am not ever able to measure absolute voltage. I can only measure relative voltage relative to the 0 point. That makes sense because voltage is measuring effectively potential energy. So we have to have a 0 point. The 0 point in electrical terms is called ground. And black is the universal symbol for ground. Red is going to be the universal, well, not entirely universal symbol for hot. So red is always hot. Hot is not always red, unfortunately. And
I think you're
yeah, it is. In house wiring, interestingly, the copper wire that comes through, the bare copper wire, is the ground wire. And you'll actually have two different hot wires that are going to be out of phase with each other and oscillate between plus and minus. And the white wire and the black wire are going to be the two different hot wires. So that if I hook up my light to white and to the bare wire, then I'm going to have an AC current that is, an AC voltage that is going to oscillate between, I forget the number, but it's 117 times root 2, whatever that is, like plus 152 to minus 152, so that the average value is 117. And if I hook up the white to the black, then I can actually double that and get 240. And that's actually how large appliances like your refrigerator or your washing machine or your dryer especially are going to be wired up. So that they can get more voltage. Okay, so we're going to use now our digital voltmeter, and I'm going to attach black to black and red to red. And I usually do it directly like this, so that I don't have to worry about holding two things at once. Well, that's going to be a little unfortunate. There. Nope. There. Now my ground is grounded, and I can touch sparks. I'm not getting a voltage reading. That's exciting. What are you doing to me? This voltmeter is not delivering on its promise. It's supposed to be measuring 20 DC volts, and instead you can see that it's providing a conduit straight through for the current, and you can see that because notice that my power supply here turns off. Let's try the analog instead, see if it does any better. We'll try another little one in just a minute, but I want to see what's going on here. What may be happening rather than what it may be that this whole piece of conductive paper here is conducting too much. So let's put this on DC volts again and see what happens when I try the analog. The analog is perfectly happy. Here's what I want you to see, and we'll see this in video. An analog voltmeter, like any analog instrument, is going to use the position of some needle to tell me how much I've got here. And because we have to measure in the wild a large number of different ranges of voltage, there are going to be several different scales. And you're going to read these scales according to the number that you have here. The numbers on the scale are 10, 50, and 250 for the max. So if I'm reading 10, 25, 50, 250, or 500 volts, I'm going to go to the appropriately numbered scale and possibly multiply by 10. So since I have my indicator on 25 volts, I'm going to read the scale that says 250, and in that case I'll just divide by 10. So if I max out at 250, that corresponds to 25 volts. If my needle goes to 100, that would correspond to 10 volts, and so on. So when I actually connect here, what's my needle on? Reading that top 250 scale. .130. Divide by 10 and get 13 volts. So it looks like this power supply is doing what it needs to do. Let's give our digital voltmeter a second chance here. And rather than, well, we can keep these guys connected. Take and, nope, even when I try to measure it directly here, it just conducts straight through. So either I'm using this wrong, no, 10, try that. Maybe I was misreading the labeling here. There we go. Okay. So the digital voltmeters are much easier to work with, and we're actually going to use those for our lab. You can go ahead and hold that and read it for us. And again, I'm going to simply put the negative probe right here and ground it like that, so I don't have to worry about it. And then I'm going to take and touch the positive probe to whatever I want to read. What am I getting? 13.64. Looks like our power supply is in good working order. Now, if you take a look at what I've got here, this is called conductive paper, and it's designed so that it conducts electricity, but not amazingly well. It's not going to conduct like a metal would. If it did, you would have infinite current flow through here, and our power supply would shut down. But it is going to conduct a little bit. Because it conducts a little bit, that's going to allow the electrical potential to drop. But I've done something else, and that is that I have painted various points along here with conductive ink. Now the conductive ink, I painted it last year, so maybe the conductive ink won't be perfectly conductive, but the point of a conductor is that it allows electrons to flow freely, and because it allows electrons to flow freely, that means that the voltage should be exactly the same at all points along the conductor. That's the thing to understand about conductors, is that along every point along the conductor, nominally the voltage should be exactly the same. In practice, it'll drop a little bit. Let's see how conductive our conductive paper is. 13.63, 13.61. Ooh, that got up quickly. Oh, no. 13.60. You read it.
13.5.
Mm-hmm.
13.52. 13.51. 13.51.
Yeah, so now watch what happens when we get off the paper, off of the ink. Yeah.
12.37.
See how my voltage drops? And as I get closer to this part, well, let's go all the way to here. 2. Yep. So notice that all along this piece of conductive ink, my voltage is basically 0. And all along here, 13.5, 13.6. And if I go in between, my voltage will steadily go up from 0.14 to
2. 6.34. 8.5. 10.2.
and then
13.
you see how that goes? All right. So what if we were to plot our results? To plot our results, what we would need to do is to get ourselves a nice grid. And on that grid, we would have to then mark different points of potential. Yes?
Why is it voltage low on that line connected?
Because this is hooked up to ground, trace it back to the power supply, this is at 0 volts directly. And it's at 0 volts relative to ground. Here, this nominally should be 0. But because my ink is not perfectly conductive, it's going to be a little bit more than that. The major part of the resistance actually happens right where this thumbtack goes into the ink, right at that interface. You're going to have a little bit of a voltage rise right there. Okay? So what if I asked this important question? What is the shape of a line that is at, say, 3 volts? What if I wanted to find all the points on this paper that are at a 3 volt potential? Well, I could do it. It would be a little bit tedious, but not too bad. Go 3.6. Okay.
3.1.
Close enough. 3.1. All right. Now, where would you predict that some other points might be at 3 volts? Come show me. Here. That's it. 2.98, not bad. So we found another point that's at 3 volts. Where else? Just experiment. Take a good guess and go for it. 3.1. Oop, dropped off. So it goes out a little bit. Yep, that's exactly right. Uh-huh. Go over a little bit. But now mentally, notice what you're doing. You're tracing a curve that basically goes out like this. What happens as I go inwards? Still too hot. Yeah. Still too hot. Okay. So if it's too hot, then which way should you go? Yeah. There you go. 3.7. 3.32. Aha. And so what you're finding is, in between here, you can get to 3 volts by coming closer. And then as you move in this direction, away from the hot spot, then you can increase your distance a little bit to get out away from there. What you've just done is to trace an equipotential line for 3 volts. And that equipotential line is going to now be all of the points at which, if we released an electron, and that electron, or it'd have to be a positive charge, maybe a proton. we released a proton here, then it would head from here to the nearest ground point with an energy of 3 electron volts, just like that. 6 volts. Step up to the plate. Find us an equipotential line for 6 volts.
3.4. 5.9.
That's good.
6.9.
Now what? We got the easy one.
5.4. 7.7. 6.9. 5.15.
Here we go. And a little bit of dragging there. Yep, yep. 0.3. Yeah. Good. So we found another point. So we have here, here, and here.
So,
Mm-hmm. Mm-hmm. 5.4. 4 points. No, too close. 6.2. 6.7. Now, why did it go up as you went that way?
because I got closer to the
Yeah.
conductor.
6. Beautiful. Okay. We've got another point right there. Okay.
Here, here, 2.
5.9. It's good. That's a good guess.
5.6.
Yeah, that's good. So, just based on that limited data, generally, what's the shape of your equipotential line for
A
6?
parabola.
Yeah, it's a parabola almost. It's going to do something like that. Maybe not exactly parabolic, but something like that. What do you guys notice about the measurements on here? Anything? When he puts it down, what happens? Does it, what is
Takes
it?
time to regulate.
It takes time. It fluctuates, and it takes time to settle down to its true value. And the reason for that has to do with the contact that's made here. If notice that I'm grounded, so I'm not 0 volts. If that change? Yes, it does. But look, I'm conducting, but not perfectly. Back to my sentence. If I press hard, then it stabilizes pretty well. If I have a weak touch on it, then it sits there and flops. Okay? So you want to press with intent. You're not trying to puncture the paper here, and you don't want to go point down because you will puncture the paper in that case. But if you go sideways here and use your thumb to exert some pressure here, think chopsticks, then you're going to you think you're going to be pretty well. All right, P-Peg, you're on. Let's get an equipotential line going for 9 volts. Something like that. Go sideways. 9.9 is pretty good guess.
9.
Mm-hmm. 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 2.66, 1.28, good. 1.25, yep. 8. Yep. Okay. Mhm. Good. So based on what you've seen so far, what does your equipotential line for 9 look like?
It's like a round here.
Mhm. And what do you notice about it in comparison to the equipotential lines for 3 and for 6?
It's one.
Yeah, that's exactly right. Notice it's really tight around, for 3, it was really tight around the 0, the ground. The 6 was like so, the 9 like so. Now, I think you can get, oh, let's find a little bit, based on your observations there, make a prediction about where it's going to be out here. See if you can find some equal potential points for 9 volts.
7.2, 7.7, 8,
Uh-huh. It can. That's right. So that's interesting. Probably, would you predict voltage would be lower or higher down in this region right over here? Lower? Test it.
5.6.
Yep. So we actually don't have any equal potential, we don't have any 9-volt things over here. Can you find any? Where might we go to find some? Back that way. 8.5.
8.9.
Aha! There we go. So our equal potential line is actually now doing, can you trace it with your finger? How the equal potential line comes down? Yeah, it's going to do something like that. That's exactly right. Very, very interesting.
That's because you have the 2 positives on the side and 1 negative.
Yeah, that's exactly right. Bulu, you're on for 12 volts. Twelve is going to be interesting. First of all, let's remind ourselves of what the conductive ink is. Go ahead and put your probe right on the conductive ink.
13.3.
Yeah. So we're looking for 12.
12.1. 12.1.
Good. So already, what do you think is going to be true about 12? Something like that. Okay. Go ahead and find some 12-volt points. Mm-hmm. Good.
12.
A little bit firmer so that you can get good contact.
11.8.
See how it stabilizes now?
12.1. 11.8. 12.25. 12.7.
Mm-hmm.
The higher you go to the corner, the higher the positive charge is.
So you want to think about it, go ahead. You don't want to think about it so much as charge just residing. So this is not actually a static situation. Instead, what you're having is charge flowing. Benjamin Franklin is going to establish a convention that charge goes from plus to minus. The reality, he had no way of knowing this, but the reality is that electrons are actually going from minus to plus. But we visualize it as charge going from plus to minus, and it doesn't hurt. So
12.1.
picture this as a dynamic situation in which positive charge is going to the ground at all times. And that flow of positive charge is what creates the voltage differentials.
12.1.
Okay, so it looks like you've mapped out pretty well what a 12-volt equipotential line looks like on the inside. Describe that shape with your finger. Mm-hmm. Something like that. I think it's a little shallower in here, right? So test that again. Just maybe my memory is bad. Pretty similar. There we go. So you see how it's more shallow like that when it comes out. What about on the outside? Try it. Can't hurt. You will not blow anything up in this lab.
He promises.
Very interesting. Okay. Find a point of 12 volts potential in this region right here. Good. So in other words, as you come out, trace with your finger how the potential line goes. Yeah, you can extend it. Absolutely.
So does the charge just go to the end of the paper? Get burned off.
Yeah, something like that. Kind of goes in to here and like that. I was referring to Olu. Your question was?
Does the charge like go out to the end of the paper and then just disappear into the cork?
No, actually it doesn't. The cork is a good insulator. What ends up happening, the fate of all the charge that comes out the plus, of course we understand it's a fiction, comes out the plus is ultimately to drain down into this right here. So it will travel along
So if
paths.
you
Mhm.
touch the cork, there's no charge in it though.
Nope. If I go to here and test, 0.
Okay.
Nothing. The only place where I get potential is along the equal potential, is along the conductor paper.
Okay.
That's good. That's very good. We've got about 5 minutes. Here's what I want to do. I want to draw some equal potential lines on the board and show you something very fascinating that relates the equal potential lines to electric field. Amanda, thank you. Yeah, I know that was a pain in the neck to hold back. Well, no one's gonna watch Okay, are we recording? We are recording. All right. So here's what I want to show you. If I were to take a point charge and draw equal potential lines around that point charge, the first thing that I would notice is that the potential is going to drop off as I go out. So that if this is maybe 700 volts or something like that, then if I double the distance, I'm going to go to half that voltage, because remember that the voltage around the point charge is kQ over R, so if you double the R, you half the voltage. And if I triple the distance right here, then I get 1/3 of the voltage, which would give me 230 volts, just like that. Here's the thing that I want you to observe, and that is that if I were to also draw field lines on this, that the field lines would come straight out from my positive charge. And what do you notice about those field lines geometrically in relationship to the equal potential surfaces? Yeah, it highlights. What is the angle between here and the tangent to the equal potential line? They're perpendicular. That's exactly right. Field lines and equal potentials, field lines and equal potential lines will always make right angles with each other. And the reason for this is really simple. The field lines are going to point in the direction of steepest drop off in voltage. How about I say steepest descent? We understand that means drop off in voltage. So that when I am mapping an equipotential line, what I'm really doing is also mapping the electric field. To get the electric field, all I have to do is to maybe start at this point, measure the voltage, and do a little bit of experimenting to find which way my voltage drops the quickest. And that is the direction that the electric field will go. Or alternatively, I could find an equipotential line and draw the normal to that curve, and ta-da, I've got my electric field. So what the equipotential lines do for us then is several things at once. First of all, they directly find voltages, they map out voltages for us. What do these curves remind you of that you might have seen in life?
Like in a circle.
Yeah, they do remind you of the unit circle, but if I take our conductive ink thing right here, all of a sudden we're not doing circles anymore. Here was our 3-volt equipotential line, right? And here was our 6-volt equipotential line, and our 9-volt kind of did this, right? And our 12-volt was more like so. What does that look like? Hint. Voltage is like elevation.
Oh, topographical map.
Yes, this looks like a topographical map. I sure can. This looks like a topographical map where we've got 12 volts, that's a high point, right? And now we're going to go downhill to 9 volts, down to 6 volts, down to 3 volts, and we get to 0. Ta-da! And we can now map our electric field just by going right to it. And that, here's our normal here, and our normal here, and our normal here, and now we've got a nice electric field line that goes from here down to here. That is cool stuff. I'll see you tomorrow. We'll do this in the lab.